quantum behavior at room temperature? That flips the script on what many physicists thought was possible. But here's where it gets controversial. Researchers have now shown that a tiny, not quite round nanoparticle can display unmistakably quantum rotational motion at ordinary room temperature, without chilling the entire particle near absolute zero. What they did, in plain terms, the team trapped an elliptical nanoparticle inside an electromagnetic field. Using precisely tuned lasers and a clever mirror setup, they drained energy from the particle's rotation until that motion was pushed down to almost the pure quantum ground state, the quietest possible quantum wobble. The twist? The particle's overall temperature stayed scorching, hundreds of degrees hot, while its rotation as a quantum degree of freedom effectively froze. Why this matters? Redefining the edges of quantum physics. For decades, the big question has been, where does the quantum world end and the classical world begin? If quantum effects only survive in ultra-cold, ultra-isolated atoms and molecules, that's a big hurdle for future quantum technologies. But if larger objects, still microscopic, yet vastly bigger than atoms, can keep their quantum behavior in everyday conditions, the door to practical devices opens wider. Enter those large quantum objects, glass spheres around 100 nanometers across. That's more than 1,000 times smaller than a grain of sand, but huge by quantum standards. Scientists have long wondered whether such particles can show genuine quantum traits outside deep cryogenic conditions. A collaboration between ETH Zurich and theorists at TU Wien has now delivered a breakthrough. They've demonstrated that the rotational vibrations of these nanoparticles obey quantum rules not only near absolute zero, but also at room temperature. And this is the part most people miss. They didn't cool the whole particle, only its rotation. A quick primer. Vibration quanta explained. In daily life, motion looks continuous. A clock's pendulum can swing a little or a lot. You decide. Quantum mechanics rewrites that story at very low energies. Certain motions are quantized, meaning the system can only occupy specific energy steps. There's a lowest rung, the ground state, then the first excited state, then the second, with nothing in between. Even more curious, a quantum object can be in superpositions, a blend of different allowed states at once. Getting a nanoparticle to reveal those quantum fingerprints is notoriously hard. You need to isolate it from its environment, let it float without disturbances, and traditionally cool it to within a hair's breadth of absolute zero, negative 273.15 degrees Celsius, to suppress classical noise. How they isolated rotation while everything else stayed hot. The new trick targets just 1 degree of freedom, rotation. By using a slightly elliptical nanoparticle, the researchers ensured it naturally prefers to align and rotate in an electromagnetic field. Then they used light as both a scalpel and a siphon. The lasers can either feed energy into the rotation or bleed it away. With a purpose-built mirror arrangement, they biased the process so energy is removed much more often than it's added. Over time, the rotational motion loses energy until it sits almost entirely in the quantum ground state. This demanded solving thorny theory questions, especially about laser-induced quantum noise. The unavoidable jitter in light that can heat or cool different motions. Controlling that noise was essential to get the rotation cleanly into a quantum regime without collapsing it back into classical behavior. Record-setting quantum purity without cryogenics. The outcome? The particle's rotation was cooled to near pure ground state, while the particle as a whole stayed blazing hot. That sounds paradoxical, but here's the key insight. Different motions, translation, rotation, internal vibrations are distinct degrees of freedom. You can selectively tamp down the energy of one, rotation, without touching the others, like internal heat. In effect, the rotation freezes, even though the particle is thermally agitated. Why this is a big deal? It's a practical route to studying quantum effects in bigger systems at room temperature. It sidesteps the need for full object cryogenic cooling, which is costly and complex. It sharpens our tools for future sensors and quantum devices that rely on controlling specific motions with extreme precision. But here's where debates will flare. Does cooling a single degree of freedom to its ground state count as achieving a genuinely macroscopic quantum state? Or is it still too limited? Should we demand multiple degrees of freedom in the ground state to claim a true step toward macroscopic quantum mechanics? If one can ground state cool rotation at room temperature, what stops us from doing the same for translation or internal modes, technical hurdles, or fundamental limits? Could this method blur the classical quantum divide enough to challenge long-held intuitions about when decoherence wins in hot environments? Reference: High-Purity Quantum Optomechanics at Room Temperature, Nature Physics, August 6, 2025. Authors: Lorenzo Dania, Oskar Schmidt-Kremer, Johannes Piotrowski, Davide Kendoli, Jayadev Vijayan, Oriol Romero Isart, Carlos Gonzalez Ballestero, Lucas Novotny, Martin Frimmer. DOI 101038/S41567/025769. Your turn. Agree or disagree? Is selective ground state cooling at room temperature the breakthrough quantum tech has been waiting for, or is it a niche trick with limited real-world payoff? Should the bar for macroscopic quantum behavior be raised to include multiple degrees of freedom, or even entire objects at once? What application would you bet on first? Ultra-sensitive rotation sensors, quantum-limited gyroscopes, or something entirely different?